Quantum mechanics is full of contradictions that feel almost impossible to reconcile. On one hand, quantum states such as superpositions and entanglements are notoriously fragile. A single disturbance, a stray photon, a tiny vibration, or a measurement can collapse them instantly. This is why building a quantum computer is so difficult. The very effects that make it powerful vanish when touched by the slightest noise. It feels as if the quantum world is built on glass threads that snap as soon as we try to hold them. How, then, can such fragile rules form the foundation of our solid, dependable universe? Paradoxically, atoms themselves are quantum objects, yet they are incredibly stable. The hydrogen atom, the simplest of all, is described by a quantum wave function, where an electron orbits not like a planet around the sun, but as a standing wave of probability around the nucleus. According to classical physics, an electron should spiral into the nucleus in a fraction of a second, radiating energy as it falls, but quantum rules forbid this. Electrons can only occupy discrete energy levels, and the lowest one is perfectly stable. This is why matter does not collapse, and why atoms can endure for billions of years. Doesn't it seem ironic that the very framework producing fragile states also guarantees the robustness of everything we touch? The key lies in scale and structure. Isolated quantum states are fragile because they exist in a kind of limbo, balanced between possibilities until the environment forces a choice. But when many quantum rules combine, electrons locked into shells, protons bound by the strong force, and conservation laws restricting decay, the result is stability. A lone violin string quivers at the slightest touch, but a whole orchestra playing together can sustain a resonant harmony that fills a hall. In much the same way, the collective behavior of countless quantum particles builds the resilient world we inhabit. There are little-known examples that reveal this contrast vividly. Entangled photon pairs can lose coherence in a fraction of a second if not shielded, yet a diamond crystal, made from countless carbon atoms bonded by quantum mechanics, can sit unchanged for billions of years inside Earth. Neutron stars push this stability to an extreme. They are colossal assemblies of quantum degenerate matter that remain intact under gravity so fierce it would crush anything else. Isn't it astonishing that quantum fragility, multiplied and organized, becomes cosmic endurance? The paradox remains. The smallest scales are ruled by fleeting, unstable states, while the larger scales they compose exhibit astonishing permanence. Perhaps the answer is that fragility and stability are not opposites but partners. Fragility allows quantum systems to explore possibilities, while stability emerges when laws and symmetries lock those possibilities into patterns. Out of this tension comes a universe that is both delicate and durable, where fleeting sparks of quantum uncertainty weave into the long-lived fabric of matter. The question lingers: is stability just frozen quantum fragility, or is fragility the necessary foundation without which stability could never exist? Quantum states such as superposition and entanglement are famously delicate. Interactions with the environment cause decoherence, collapsing the wave function into definite outcomes. Even a stray photon or vibration can destroy coherence. This fragility is why building a quantum computer is so challenging. At the microscopic level, quantum systems seem ephemeral and unstable. Yet, paradoxically, these fragile principles also underpin the stable structures of matter. Entangled photons can lose their quantum link if disturbed by air molecules or imperfect detectors. It is like trying to keep soap bubbles intact in a windy room. Beautiful, but easily destroyed. Despite quantum fragility, atoms are remarkably stable. Electrons orbit nuclei in quantized energy levels that prevent continuous energy loss. Quantum rules forbid them from spiraling into the nucleus, creating enduring atomic structure. This stability arises not from classical certainty, but from quantum restrictions. The Pauli exclusion principle and discrete energy states protect matter from collapse. Atoms therefore persist for billions of years, forming the foundation of matter. Hydrogen atoms, created after the Big Bang, still exist today, over 13 billion years later. It is like fragile rules of a game that, once followed, produce a structure that lasts indefinitely. The Pauli exclusion principle states that no two fermions, such as electrons, can occupy the same quantum state. This rule creates order and stability in atomic structure. Without it, electrons would collapse into nuclei, and matter as we know it would vanish. Instead, electrons fill distinct energy levels, creating the periodic table and chemical diversity. Fragile wave functions are stabilized by this strict quantum law. Stability thus emerges from a rule that enforces separation. The structure of carbon atoms essential for life is determined by the exclusion principle shaping electron shells. It is like students filling seats in a classroom. Order is maintained because no two can sit in the same chair. The Heisenberg uncertainty principle prevents particles from having both exact position and momentum. This intrinsic uncertainty keeps electrons from collapsing into nuclei. Instead, they maintain stable clouds around atoms. Thus, what appears as fragility, a limit on precision, becomes a source of stability. The very fuzziness of quantum mechanics generates lasting order. Uncertainty, paradoxically, is what guarantees structure. Helium atoms remain stable because electron uncertainty balances attraction to the nucleus with resistance to collapse. It is like a tightrope walker wobbling slightly but never falling. The instability itself keeps balance. Individual quantum states collapse under measurement or environmental noise. But when vast numbers of particles interact, their collective behavior averages into stability. Decoherence that ruins superpositions at the microscopic scale produces definite outcomes at the macroscopic scale. What is fragile alone becomes stable in crowds. Emergent order is born from microscopic instability. This is why our world appears classical and predictable. A single quantum particle is fragile, but a diamond crystal made of trillions of atoms is solid and stable. It is like grains of sand, individually shifting, but together forming a sturdy beach. At even deeper levels, nuclear forces stabilize matter further. Protons and neutrons bind in nuclei with incredible resilience, resisting decay for billions of years. Quantum chromodynamics governs this stability despite underlying quark interactions being highly dynamic. The same paradox repeats. Fragile quantum rules produce cosmic endurance. Without nuclear stability, stars and planets could not exist. The small-scale instability yields a large-scale universe. The proton is so stable that no decay has ever been observed despite billions of years of testing. It is like countless flickering candles arranged in a pattern that together form an unextinguished beacon. Life depends on the paradoxical stability of atoms and molecules. DNA, proteins, and cells rely on stable chemical bonds that persist long enough for evolution to act. Fragile quantum rules guarantee that these molecules retain their structure. Without atomic stability, life could not form, yet without quantum fragility, chemistry would lack complexity. Fragility and stability interlock to create conditions for biology. Stability becomes the stage where fragile events produce living systems. The double helix of DNA depends on stable hydrogen bonds shaped by quantum rules. It is like writing with chalk. Fragile particles form durable words on a board. Modern technology exploits both sides of the paradox. Quantum computers seek to preserve fragile coherence to perform calculations beyond classical machines. At the same time, everyday electronics depend on the stability of atoms and semiconductors. Engineers must protect fragile states while trusting the larger stability of matter. Both extremes are harnessed to advance civilization. Fragility and stability coexist as resources. Superconducting qubits must be shielded from noise, while silicon chips remain stable in phones for decades. It is like building with both delicate glass and durable stone. Each serves a different purpose. The paradox is that fragility at the smallest scale produces stability at larger scales. Quantum states collapse easily, yet their very rules enforce enduring structures. Without fragility, there would be no definite outcomes. Without stability, no lasting universe. Atoms embody both sides of the paradox. Ephemeral in principle, but eternal in practice. The instability of quantum processes becomes the foundation for order and permanence. Fragile beginnings give rise to enduring worlds. The universe is filled with stable hydrogen atoms, even though their behavior is governed by fragile quantum rules. It is like a mosaic made of fragile glass pieces that together form an image that lasts for centuries.